We will now switch to mathematics. I welcome to the stage Professor Bruno Loff from LASIGE and CMAFcIO, our last ERC awardee from European Research Council, and according to whom mathematics is Sudoku. So let's learn why. Let me put your presentation here. There it is.
Okay, so there's several ways of giving a talk, and you'll realize that mine will be a bit different. So I'm not very good at doing these like broad talks, and then we did this. And so I kind of like to invite you to sit by my fireplace, and I will tell you something which will hopefully trigger your mind a little bit. So I'm guessing most people here have learned some mathematics, and I'd like to make the preposterous thesis that mathematics is actually Sudoku. I hope you know Sudoku. It was popular, more popular maybe 10 years ago than it is now. So this is a Sudoku puzzle, and the idea is that you have to fill in the missing entries in such a way that there's no repeated numbers. So you can use numbers from 1 to 9. And there can be no repeated numbers in any row or in any column or in any block of 3 by 3. And that's it. And that's your task. It's a puzzle. It was popular there, so you can buy Sudoku books to practice. And once you start playing around with them, you realize that there starts to be some kind of logic, as the fact that these numbers are here implies somehow that I cannot put a number, such and such number here, and that in turn, together with this other one, implies that I must put a 5 there. Stuff like that. Okay, so it's fun game to play around, and I did my fair share of Sudoku. And I would like to actually claim that all mathematics is Sudoku. Before I can kind of defend this claim, I'll have to try and say something about what is mathematics, right? Otherwise, okay, so I would like to say that mathematics is the branch of human knowledge that studies that minuscule part of human experience that can be described and talked about with complete rigor and precision. The mathematical objects are those concepts that can be precisely defined using language. Mathematics is the study of mathematical objects using that part of language which lacks any ambiguity. And I'd like here to make a distinction between what I'm trying to come to, which is some kind of broad definition of mathematics, and the actual practice of mathematics, which is itself quite different. So let me give you some examples of mathematical objects. We all know a few. There's numbers, there's functions, there's geometric objects, algebraic objects, combinatorial objects, or for example, something more connected with physics, could be a mathematical model of an atom, and so on. And of course, there's also non-mathematical concepts, such as love, justice, health, or even the concept of an atom, which is itself not mathematical, although the various different models of an atom that we may have in mind are themselves mathematical. So you see that in the non-mathematical side of this table is essentially all the really important stuff. Okay, so these are the mathematical objects. And now, what is mathematics? Well, we study these objects using, like I said, that part of language which has no ambiguity. So we use logical deduction, examples, counterexamples. We represent some objects using other objects. We use algorithms for summing, multiplying, and so on. But all of these things can ultimately be reduced to logic. So it's fair to say that mathematics is logic, and I will get into that a little bit. But before, I'd like to distinguish here my attempt at defining mathematics from what actually is mathematical practice, which is something else entirely. So mathematical practice includes drinking coffee, feeling frustrated, scribbling indecipherable symbols, even indecipherable to yourself just a few days later, making trivial logic mistakes, feeling completely lost, having stupid ideas, sharing your stupid ideas with your colleagues who take all of 15 seconds to understand why your idea is really stupid and pointing it out to you with friendly, kind patience. And then, so the mathematicians are all laughing, as you could see, drinking more coffee. And then occasionally you're a bit lucky and you find something. So let me say, why is mathematics ultimately logic? This is a highly non-trivial fact. It has been known for the vast majority of the history of mathematics. And you could say I'm being a bit simplistic, but at some point this guy, Frege, came along, and after many, many attempts by other people, he kind of got a very good attempt at formalizing mathematics. He came up with a language of sorts, where, as far as he could tell, all the mathematics that he knew could be written in. And of course, when he came up with it, there was these kind of awful diagrams. And now we've kind of simplified it a little bit. So an example of a, so this language that he came up with, we call it nowadays first order logic. And an example of a sentence in first order logic would be this one. It says that for every x, if ax is true, suppose that, so there's this implication, which is kind of the outer one. So suppose that the following is true. For every x, if ax, then bx is false. Then that implies that there's not exist an x where ax and bx are both simultaneously true, right? And if you manage to parse that, you're going to go like, oh yeah, that makes sense. And actually up above, we have kind of a proof of this statement using simple logical rules such as generalization and modus ponens, actually maybe even modus ponens, instantiation and so on. Okay. So what's in the bottom is some kind of statement using first order logic, and above you have a proof, which uses some kind of logical rules. And it is broadly believed that every single work of mathematics ever done or yet to be done can ultimately be written as a mathematical proof that uses the language of first order logic. And I'd like to point out how absolutely amazing that is. So there is no other human discipline for which some kind of such broad, all-encompassing statements can be done. Like imagine trying to do this for psychology, for example. Every single sentence in psychology is going to be written using these words. And you can combine these words using these particular rules. There's nothing like that for any other field of human knowledge. And that makes mathematics very special. And in light of this astounding fact, one can understand that the job of a mathematician is ultimately to find mathematical proofs. So the question comes, how hard is it then to find mathematical proofs? Now, let's say one person, very important person to first ask this in some kind of methodical way was David Hilbert. He asked, how hard is it to find a mathematical proof? Is there some kind of method that we can follow? Nowadays, we call these things algorithms, but he called them effective methods. So is there some kind of algorithm that we can follow? So I give you some kind of statement, and you run your method, and after that, then it will spit out an answer and saying, yes, there's a proof for this, or no, there's no proof. Alan Turing, the person who invented the computer, actually did so in order to show David Hilbert that there was no such method. We could call this Turing's theorem, although Church formally proved it before in a less convincing way, but logically equivalent. So Turing would show that there exists no algorithm that will succeed in finding all proofs that exist. And in doing so, he invented the computer, and everyone here has a computer in their pocket. And this was the guy who invented it. And he invented it in order to answer Hilbert's question. That's why he invented the computer. Now, Kurt Gödel came along. He's also a very important fellow for other reasons. And he asked a couple of decades later, okay, so there's no algorithm to find a proof, but suppose that I'm okay with one thing. I just want to know if there's a proof up to a certain length, n. So these proofs have sizes. You can kind of bound the size of the proof, and you can ask, suppose I only want to know if there's a proof up to a certain length, n. So I want to find a proof of this length up to length n if one exists. And now, obviously, there is an algorithm that does this. Namely, I go over every single proof of length n and see if it's actually a proof of my statement. This is what's called exhaustive search. It's an algorithm of exhaustive search. And of course, you can do this, but it takes a whole lot of time. And what Gödel asked is, can I do it efficiently, say in time n squared or n to the c for some costs? where n is the length of the proof I want to find. So this is Gödel's question. Can we find a proof of length at most n if one exists in time n to the c for some constants? Gödel was asking ultimately if there exists an efficient algorithm for automating the job of a mathematician. Computational complexity, which is the field that I study, studies this question and other questions like it. It is a theory that allows us to understand how difficult or complex are various problems, and this is one example of a problem we could study. Now, enter Sudoku. We all, or maybe hopefully most of us, have seen this 3x3 and or 9x9 Sudoku puzzle, right? But we could generalize this to any side, right? We could define 16x16 Sudoku or 25x25 Sudoku. So generally, there's a Sudoku for every number n, and it's an n squared by n squared board. You know, to fill the board with numbers between 1 and n squared, so that in each row, there's no repeated numbers, in each column, there's no repeated numbers, and in each block, there's no repeated numbers, right? So that's n by n Sudoku. And now I'm ready to defend this claim that mathematics is nothing but Sudoku. So as it turns out, the theory of computational complexity can prove the following, I think, remarkable theorem. There exists an efficient algorithm for solving Gödel's problem, meaning there exists an efficient algorithm for finding proofs up to a certain length. Or in other words, there exists an efficient algorithm for automating the job of a mathematician if, and only if, there exists an efficient algorithm for solving n by n Sudoku puzzles. And proving this is not obvious. It took several years. So it's actually easy to show that if there exists an algorithm for doing proofs, then there exists an algorithm for solving Sudoku efficiently, because you can actually essentially write the Sudoku puzzle using first-order logic. That's not very hard to do. The other direction was actually quite hard, though. So first, this very important theorem by Cook and Levin showed that finding proofs can be, well, if you're going to find any proof, you can actually find proofs of simpler statements. Like these are very simple statements. And then this somehow translates into some graph where you have edges, and you would partition the graph into triangles. And that was 81, and then 82. This kind of, you show that, you know, these like triangle partition problem can be represented using a Latin square completion problem. I don't know if any of you have seen Latin squares, mathematicians probably have. And then in 2003, this Yato fellow showed how Latin square completion can be represented as a Sudoku puzzle. So there's this long line of, we call them reductions, showing how actually finding proofs, if there's an efficient algorithm for Sudoku, you can run over this set of reductions and eventually find one for solving proofs. And as a conclusion, mathematics is good. Okay. So in complexity theory, we have a way of understanding the relative difficulty of solving a computational problem. So relative to each other, Sudoku and mathematics have the same difficulty. And we have seen that the two problems, finding proofs and solving Sudoku puzzles, have the same difficulty relative to each other. But what about in absolute terms? I mean, so mathematics is just as hard as Sudoku, and you could ask yourself, well, but how hard is it actually? Is there an efficient algorithm or not? Of course, if there is, so now we can rephrase Gödel's question and say, well, does there exist an efficient algorithm for finding proofs, or equivalently for solving n by n Sudoku puzzles? I mean, we still haven't answered the question. We just said that the answer is the same for both. Okay? This is what is known today as the P versus NP problem, which is considered maybe one of the most important problems in mathematics. And okay,